right, hello, welcome back. When we finished on Monday, I had introduced this biological version of the Claisen reaction, and I had asked you to think through it. I said that it was going to be the reaction of this ester as the electrophile with the molecule on the right, which I called a masked enolate. And the reason it's a masked enolate is because it's a beta keto acid, which can decarboxylate. I am recording. So I said the first arrow was that this oxygen is going to kick down and electrons are going to go onto the alpha carbon of the enolate to generate the purple thioester enolate, and we lost CO2 in that process. Then that enolate goes and reacts with the carbonyl carbon of acetyl-CoA, and that's the step that should look like a Claisen reaction. One enolate from a thioester attacking the carbonyl carbon of another thioester. Here in red is the new bond we made. We make that bond between the carbonyl carbon of the electrophile and the alpha carbon of the enolate. So this is your intermediate, and it turns out that the negatively charged thiolate ion is a decent leaving group, so electrons kick down and the coenzyme A conjugate base, negatively charged thiolate, leaves as a good leaving group. And again, in our product, we've made a new bond between the alpha carbon of what was our enolate nucleophile and the carbonyl carbon of our electrophile, which is now a beta carbon, and the product is a beta keto thioester. This is the first step in fatty acid synthesis, and nature will go on through subsequent steps to actually reduce that ketone to an alcohol, then do an elimination reaction, then reduce again. And stay tuned, because we will talk about all of these steps later. But ultimately, that's going to convert our starting material, which just had 2 carbons, and then our other starting material, which had 3 minus a CO2, into a 4-carbon chain. And then it turns out that once biology's gotten here, you can take this thioester, move it over here, and have this be the starting material, and go again to put another 2-carbon chunk onto that chain. And by cycling through these reaction steps, biology takes simple precursors like acetyl-CoA and makes quite a long hydrocarbon chain, which is where fatty acids and lipids come from. Okay, questions about the Claisen reaction? Yes, please. We haven't learned how you get rid of that oxygen. It's not that hard. If you were going to reduce, but we'll talk about it later, just as a preview, if you were going to reduce this ketone, and you were biology and you're not going to use lithium aluminum hydride, what's your hydride delivery reagent of choice for biology? NADH, yep, and it's going to be hydride delivery to that carbonyl carbon to turn it into an alcohol, and then we'll talk more, but that's sort of the first step. Okay, others? Okay. We got one more new reaction to do, and then this chapter crescendos with a series of multiple reactions that gives you a beloved 6-membered ring product. So you got to stay tuned for that one. Before we get there, here is the new reaction for today. It actually is not really a new reaction. Instead, it is an example of an old reaction, which is called conjugate addition, or we've called it 1,4 addition. We previously saw an example of 1,4 addition in chapter 13, where we learned that cuprates will react with the beta carbon of alpha beta unsaturated carbonyl compounds. Here's an organocuprate, and here's the attack on the beta carbon to give us an enolate intermediate. And we won't belabor the point too much. That enolate can be protonated to give you the final product on either, that enolate can be protonated either on that alpha carbon or on the carbonyl oxygen. If it gets protonated on the carbonyl oxygen, that's fine. It rapidly tautomerizes to the ketone product. So we'll just show an abbreviated mechanism that avoids worrying about that tautomerization step that we've already talked about. But this is the product of conjugate, got it wrong, sorry. This is the product of conjugate addition to that alpha beta unsaturated carbonyl compound, right? Here is the carbonyl carbon, here's the alpha carbon, here's the beta carbon, and here is the new bond that we made. And so that's an example of a conjugate addition reaction that you've seen before. What we're going to do now is simply to do a conjugate addition reaction, only we're going to use an enolate as a nucleophile. So the Michael reaction is generally considered to be conjugate addition reaction in which the enolate is the nucleophile. So an example of a Michael reaction would be, let's use this beta diketone as our starting material, or our enolate. We're going to do that simply so that it's unambiguous what the enolate is. And for the Michael reaction, you can use, like the aldol reaction, you can use a simple base like hydroxide. The first step is to deprotonate at the alpha carbon. So what we're doing now is we're preparing the enolate nucleophile. We're going to deprotonate at the alpha carbon to generate this intermediate. Okay. And then we can introduce our alpha beta unsaturated carbonyl compound as an electrophile. So it doesn't really matter what we choose at this stage. Let's just choose a simple aldehyde. And carbonyl carbon, alpha carbon, beta carbon. As before with the cuprate, we're going to have the enolate attack at the beta carbon, and electrons from that bond between alpha and beta carbons are going to go onto the alpha carbon. So I'm going to draw the electrophile portion. Here's the alpha carbon, lone pair electrons there. Here's the beta carbon, and in red is the new bond between the beta carbon of my electrophile, and then over here, the beta carbon is bonded to blue alpha carbon of my enolate nucleophile. Okay, although the blue alpha carbon of our enolate, now that we've made this new bond, is now what we would call gamma to the black carbonyl carbon. Okay? So this should be exactly the same as we did before with cuprates, highlighting in purple the enolate nucleophile and where it ends up, and then highlighting in orange the alpha beta unsaturated carbonyl compound and where it ends up. Finally, we protonate on the alpha carbon. Of course, we've got plenty of options for that because this reaction happens in water. So likely we remove a proton from water. And then our final product will be this, with protons on the alpha carbon, which I'm going to just omit Okay? So this is a Michael product. And in principle, moving forward, the reaction's not that difficult. Though sometimes you are right to worry about other options. For example, some of you might have looked at this aldehyde and said, isn't it reactive at the carbonyl carbon too? Why doesn't the enolate attack the carbonyl carbon? That would just be an aldol reaction, and we know those reactions can happen, right? Why aren't we doing that here? Presumably because this isn't just an aldehyde or a ketone, it's an alpha-beta unsaturated carbonyl compound. So is it a decent assumption that if one of your starting materials is an alpha-beta unsaturated carbonyl compound that you should be thinking about a Michael reaction? Yes, that's as far as I can tell in your text. There aren't any examples they give you where this is a starting material and you're expected to attack at the carbonyl carbon rather than the beta carbon. At least not in the context of enolates as nucleophiles. Okay. Some other things that you might be worried about. You'll notice that I chose this alpha-beta unsaturated carbonyl compound so that there weren't any alpha protons here. I did that so you wouldn't worry about the possibility of your OH minus deprotonating at that alpha carbon. I also deliberately chose the enolate so that the proton on the enolate would be pretty acidic, so that there would be no question as to which proton the hydroxide removes. And these are choices that sometimes you have to make as a synthetic organic chemist. If you can design your system to avoid undesired side reactions, that's probably best. And near as I can tell, when your text wants you to do a Michael reaction, in general, they'll use an alpha-beta unsaturated carbonyl compound as the electrophile. And in many cases, when they're focused on only the Michael reaction, they will use nucleophiles like this, which have especially acidic alpha protons. One other important aspect of thinking through the Michael reaction is looking at a Michael product and being able to think backwards to what the starting materials would have been. It's obvious here because I've highlighted them. Answers are always obvious in retrospect, but I'm going to use, well, either Greek letters or a numbering scheme to help you recognize Michael products. So if you look at the Michael product, notice that the new bond that you make is always between the beta carbon and then the alpha carbon of another enolate. Or, as I pointed out, the new bond that you make in a Michael product is this bond between beta and gamma carbons. If you see a product that has a carbonyl on the delta carbon, that's a pretty good indicator that it could have been a Michael product. I'm talking about, you remember when we learned about the aldol reaction, I said if your product is beta hydroxy ketone, that's probably an aldol product. For the Claisen reaction, I said if it's a beta keto ester, it's probably a Claisen product. Similarly here, for the Michael reaction, you're going to have a carbonyl on the delta carbon. The other way your text talks about this is to call this product a 1,5-diketone. So if your product is a 1,5-diketone, you can think, I maybe could have made that via the Michael reaction. And in that way can build up sort of reasonable retrosyntheses. Okay, questions? Yeah?
Would there still be an acidic proton between the diketone?
Yeah, would there still be an acidic proton between the diketone? Yes, there's one there that I haven't drawn. And presumably, after we protonate on this alpha carbon, presumably OH removes that proton, and there we sort of sit for a while, not doing anything because that conjugate base is pretty stable. Then gentle acidification, gently adjusting the pH below whatever the pK of that proton is will yield that desired product. Others, yeah? Does it have to be a ketone as a nucleophile? Could you use a diester? Sure. Yep, that would be fine.
At that point, could you do decarbonization?
Could you? Oh, that sounds fun.
No, it doesn't.
Our friend here is writing good exam question now. I think you're asking, what if this were a diester? Could you do the Michael reaction, then hydrolyze the ester, decarboxylate, and conceal all that you had done? Probably. Okay, what else? Don't smile like that. Could you draw that for us in detail and show us how it would appear on an exam? I think that's probably too complicated for the Michael reaction the kind of question I would give. But yeah, I saw another hand. Yeah.
So just to summarize, we can recognize this product if a carbon is gamma to one carbonyl carbon and then
Alpha to another. Yep.
Okay.
Yeah, you'll recognize this by finding a carbon that's alpha to one carbonyl but gamma to another. That's the same way of saying, that's a different way of saying a 1,5 dicarbonyl. Okay, I saw another hand. Question withdrawn. I backed off on that whole decarboxylation thing in the Michael reaction, so that question was withdrawn maybe. All right. Okay, we're going to have some more time to experience the Michael reaction, but I'm actually going to move on because I want to show you the Michael reaction in the context of a larger reaction. So what we're going to talk about now, which you will likely hate, is the so-called Robinson annulation. So we like nominalizing words. What does annulation mean? That is the process of making a ring. The root there is from, I think, the Latin for a circle, or other words in English. Annual is something that comes around every year, right? Spanish speakers, the word for a ring is anillo, right? So we're going to be making a ring, and in particular, the product that you want to forged in the fires of Mount Doom. No, I mean maybe that seems like it's on brand for organic chemistry. Specifically, the product of this reaction is always a 6-membered ring, and it's a 6-membered ring that has a double bond between carbons and a conjugated carbonyl group. So the basic structure you're looking for as a product for this reaction is that. Okay? If you know that from the beginning, it'll be easier to recognize when you need to do the Robinson annulation. This is named after the person who discovered it. And again, the term annulation just means ring making. Right, so, all right. In reality, though, this reaction is just 2 steps, or just 2 reactions tied together that you've seen before. So the first is a Michael reaction, and it is immediately followed by an intramolecular aldol. Okay, so let me give you an example of a Robinson annulation. And let's start with just a simple ketone. Let's use acetone. And then let's use this alpha beta unsaturated carbonyl compound. All right. And maybe for fun, we'll label the electrophile, which is going to be our alpha beta unsaturated carbonyl compound, in yellow, and the thing that's going to be our nucleophile, where we're going to make our enolate from, in purple. Okay? So the first step is the Michael reaction. So that's going to involve deprotonation of the purple alpha carbon using hydroxide as base. That's just boring old enolate formation, which you have seen before. And that's only going to occur to a very small amount because the pKa of a proton alpha to a ketone is around 20. So we're not forming very much of the enolate. Though, let's see, and though the stability of the products that we make are going to drive the reaction forward. So we won't worry about how we're only forming a very small amount of enolate here. Once we form that enolate, this is our nucleophile, and this is our electrophile, and this is the Michael reaction step. We're going to have the purple alpha proton attack the orange beta carbon, conjugate addition, and then electrons from the pi bond are going to go on that alpha carbon. And so here in red is the new bond that we made. I'm going to continue our highlighting so you can follow through the various parts of the molecule. I'm going to keep labeling purple alpha proton, orange carbonyl carbon alpha, and orange beta. Though now you're going to note that purple alpha is now gamma to the orange carbonyl carbon. So that's the Michael step. Questions about that? All we're going to do now is protonate on that alpha carbon to get the neutral product. And I want you to pay attention to the pattern that we fulfill when we do so. This is probably just protonated by water. And I want you to notice that the product is a 1,5 diketone. Now I'm going to continue highlighting in purple and orange. Maybe we'll use red for the new bond that we made. And you can see that the orange gamma carbon is the same as the purple alpha carbon. And our product is definitely a Michael product because it is a 1,5 diketone. Okay, so that's the Michael reaction. Questions about how we got there? Okay, now it just so happens that this Michael reaction product is symmetrical. Do you notice that orange carbonyl carbon is identical to purple carbonyl carbon? That's just an accident of the choice I made when I drew this as a starting material. It's not going to always be that way, but it happens to be that way here. All right, the next step of the reaction involves us removing a proton from the other orange alpha carbon. So we'll call it alpha prime. What we're going to do now is to do an intramolecular aldol. Now this is not new either. You have seen this before. Looking at this molecule, again, because the example I've chosen, I'm dismissing entirely by symmetry because the purple and the orange carbonyl carbons are identical. We're not worrying about whether this alpha carbon gets deprotonated versus that one because it doesn't matter, they're identical. But you faced similar problems before, and when you did, you could ask, well, if we're going to do an intramolecular aldol, which alpha carbon gets deprotonated? Is it this one or this one? If we made the enolate here and it tried to attack this carbonyl, that would be a 1, 2, 3, 4 membered ring product, probably not as stable as the 1, 2, 3, 4, 5, 6 membered ring product that we can get if we remove this alpha proton. So to some extent, you got to remember the intuition you built up about the intramolecular aldol reaction. There are other choices here, but we're going to choose to make the most stable ring. Okay, so to do that, we'll remove this alpha proton to make an enolate. And I'm going to continue highlighting things. We'll just, though I'm going to stop labeling all the carbons, we'll just call this one alpha now. Fine, I know that's bothering some of you, so we're going to call it alpha prime. And now that negatively charged carbon is going to attack the other carbonyl carbon to give us a tetrahedral intermediate. Now we sort of need to pay attention and count the number of atoms in the ring that we made. Numbering your carbons is always a good choice. Because there are 6 atoms in the ring, I'm going to just draw a hexagon before I even worry about where all the groups are. I'm going to start 1 here, 2, 3, 4, 5, and 6. I'm going to note above that 2 has a carbonyl on it. The new bond I just made is the bond between 1 and 6. Carbon 4 should have 2 methyl groups on it. And carbon 6 should have a methyl group and then our negatively charged oxygen. I will go ahead and continue to label with color the parts of the molecule that have come from the original starting materials. And I'm going to continue to highlight the bond between carbons 4 and 5 that we made in the Michael reaction, whereas this bond between 1 and 6 we made in the aldol reaction. Yes? Isn't there another methyl group on carbon 2? No, carbon 1 is that group. Oh, okay. Yeah.
Does the base matter at all with like what hydrogen is related?
Does it matter which proton the base removes?
Like the base LEA versus.
Does it matter which base you're using? In general, for the Robinson annulation, you're just using hydroxide. You could, in principle, use LDA, but it would be expensive and unnecessary. And in fact, we're taking advantage of the use of OH minus as a way to make sure we get the most stable product anyway. Okay, others? All right. So that's the aldol tetrahedral intermediate. I didn't like where that was, so now we're moving it. What do we do after an aldol reaction? Well, we protonate the tetrahedral intermediate, so we can do that with water. So that's just going to get us here. Oops. To the beta hydroxy carbonyl compound. That's an aldol product. Now the thing is that with the aldol reaction, you already know that you frequently don't stay at the beta hydroxy carbonyl compound, but instead go on to do the E1CB style dehydration to get the corresponding alpha beta unsaturated carbonyl compound. The way we do this, recall, for the aldol reaction is first you deprotonate the alpha carbon to generate the enolate. And it's then and only then that you do the elimination step where OH minus is kicked off as a leaving group. And we call this, both of these steps, an E1CB reaction. The reason we call it E1CB is because the deprotonation step is fast and separate from the elimination step. The product of that is as follows. I don't like how I drew that six-membered ring, so let's try again. Here's the new double bond we just made, and there's the methyl group. So again, I can use color to label the parts of the molecule that come from our starting materials. I can use, let's use red to indicate this bond that again we made in the Michael reaction. And then these two bonds which we made in the aldol reaction and subsequent E1CB style elimination. There is the ring. Nice engagement ring style, right? Anybody want to wear that? You can hold it in your hands and call it your precious. I know the Star Wars references work better than the Lord of the Rings references. I get it. All right, questions about that? Yes?
Can we use some reagents from Chem 351 to just do elimination on the OH?
Could you use reagents from 351 to do elimination on the OH? You could, but you don't have to because it actually happens spontaneously when you use OH minus as your base in this reaction. Notice that in a lot of these steps, we're both consuming the base and then in a subsequent step, we'll regenerate the base. In that way, this is acid catalyzed. So the acid is cheap and you don't need a lot of it. What else? Yeah?
Is there anything to stop this from attacking the OH attack the other alpha punch?
Is there anything to stop the OH at the end
Yeah.
from doing more things?
No, I'm just back at the aldol product step.
Okay. Here.
Yeah, I haven't attacked that.
Is there anything to prevent the OH from attacking this hydrogen or this one?
Yeah, that one.
Yeah, the hydrogen on carbon 5 is not acidic because it is not alpha to a carbonyl. Could this proton be removed? Sure, though it doesn't lead to elimination, and so that likely happens but doesn't go anywhere. Okay. I suppose at this stage, some of you are noticing that this is itself an alpha-beta unsaturated carbonyl compound. So some of you are wondering when the madness ends, and do we continue to have nucleophiles attack at the beta carbon? Generally not. It's not outside the realm of possibility, but generally not. Okay, what else? Yes? Is this entire reaction in equilibrium? Yes. And you make this stable six-membered ring as the product, and its stability is one of the reasons why the reaction works. I think we probably need more practice on that than what we've done so far. So what we'll actually do now is think through it backwards. No, yes. You must. We're gonna think through a different example backwards to predict what the starting materials would have been, and then having thought through it backwards, we will actually draw the mechanism in the forward direction. I think we got enough time for that. Okay, and I should say that what we've just drawn is famously the worst mechanism you could do in 352. So, I mean, yeah, congratulations, yay, hooray for you. That applause, I think, is for you, not for me having made you do it. All right, so let me draw now a product which I will tell you is the product of a Robinson annulation reaction. I guarantee you that this will be at least, not this particular example, but something in this format will be at least one of the questions on the exam, because they're so easy to write and so fun to look at. All right, here is, okay. Are you seeing that one of the skills you need to develop is the ability to focus in on the relevant portions of the molecule while temporarily forgetting about the portions that don't matter? What is, yes. Do you know how to do it yet? That's okay, we're gonna learn. What is the relevant portion of this molecule? What is the structural pattern you were looking for in a Robinson annulation product? The cyclohexenone, okay? The Robinson annulation product is always a cyclohexenone. So let's just highlight that in gray. That's not gray. Let's try again. There's your cyclohexenone. Okay, now I'm gonna just copy down up here what we drew, because this is an actual sort of nice summary of the Robinson annulation here. You can look at the Robinson annulation product, and if you're used to looking at it, you can actually tell which bonds in the product that you made in the Michael reaction versus the aldol reaction. And all you gotta do is look for the ene-one structure. I'm talking about the ketone and the double bond. And start sort of counting back from there, carbonyl carbon, alpha carbon, beta carbon. So let's do that over here. Carbonyl carbon, alpha carbon, beta carbon. Those two bonds are the bonds that we made in the aldol reaction. Okay? Has to be. Then, if you recall, on the other side, the bond between the alpha and, I'm sorry, between the beta and the gamma carbons is the bond that you make in the Michael reaction. Are you seeing how I'm using that pattern on the right and figuring out where those bonds are on the left? If you can do that, this problem is actually not as hard as it looks to begin with. Because once you've done that, you highlight this portion, and this portion becomes, this portion was the electrophile in your starting material, which, as you recall, is originally going to be an alpha-beta unsaturated carbonyl compound. And then this portion in purple and everything else that's attached to it, which we've ignored up until now, all of this is going to have been your enolate. All right. So, knowing what we know about the Robinson annulation, what was the immediate precursor? We're thinking backwards now. Right, the step immediately before the end is the step where the OH is still there. And the OH is going to be where? On that carbon, right? Now, because we don't have a huge amount of time, I'm going to stop pausing to highlight things in color. Though I encourage you to go back and do that if that's in your notes, if that's helpful to you. The immediate precursor is the enolate, and recall that the way this works is lone pair electrons on that enolate kick down and kick off the OH minus group, right? All right, what's the immediate precursor to that enolate? Just the version that doesn't have the negative charge there, right? So this is, we'll call this the enolate prior to elimination. This is the beta hydroxy carbonyl compound, and this is the aldol product. Okay? What's the immediate precursor? And remember that in the aldol reaction, we make this bond right here between alpha and beta carbons. What's the immediate precursor? In an aldol reaction, what gives you this beta hydroxy compound? On the beta, what becomes the beta carbon, we need what functional group? Has to be a ketone. How do you know it's the ketone? Because you've got the oxygen here, and then this beta carbon used to be the carbonyl carbon. Right? So on that carbon, we're going to have a ketone. How about here? What should be on this carbon, which we previously called alpha? To do an aldol reaction, what does that need to be? Enolate, right? And that reaction looks like this. Alpha carbon attacks carbonyl carbon. Electrons go out onto the oxygen to give you, oh, sure, we skipped a step, didn't we? How much do you hate me for skipping that step? Only some? Only some much, just slightly? Okay, fine. All right. So here we are. We're thinking backwards. We do the aldol reaction. We attack the carbonyl carbon to get a tetrahedral intermediate. We make a new bond between alpha and beta carbons, and the oxygen's negatively charged. Then, of course, to go a step forward from there, we simply pick up a proton from water, and that gives us this product. To get from the beta hydroxycarbonyl compound to the next step, recall we're simply going to remove a proton from the alpha carbon to get the enolate. All right. Question so far? All right. What's the immediate precursor to this enolate? We just got to make the enolate, right? Somebody's dying to tell me I lost the double bonds in benzene there. Haha, I got it before you told me. Self-corrected errors don't count, right? All right, so that is our starting material, and this is the 1,5-diketone. That is the product of the Michael reaction. And just to remind you of our initial decisions about what was going to happen here, this portion of the molecule is going to be the alpha-beta unsaturated carbonyl compound, our electrophile. And this portion is going to have been our enolate nucleophile. Okay? And the new bond we're going to make is right here. So, what's the immediate precursor to that 1,5-diketone? Remember, in the Michael reaction, a nucleophile attacks the beta carbon and the negative charge goes on the alpha carbon. So the immediate precursor has got to be this. We'll show the bond in red in place. This is the orange beta carbon. This is the orange alpha carbon. That's got to have a negative charge on it. Oops. Okay. And of course, we get from that negatively charged enolate to the 1,5-diketone by simply removing a proton from water. Okay, the immediate precursor to that should look like this. Here's the ketone, and I need a negative charge on purple alpha proton so that it can attack the beta carbon on my electrophile, which should look like this. And that mechanistic step goes as follows. Enolate attacks beta carbon and electrons go on the alpha carbon. Then the immediate precursor to that is simply our ketone starting material, which looks like this, and we'll show generating the enolate by having hydroxide remove a proton from that alpha carbon. Why do you suppose hydroxide removes that alpha proton instead of the one on the other side? It's more substituted. The other hint is you got resonance stabilization of the resulting anion on both sides, both with the carbonyl and with the benzene ring. So that actually is the most acidic proton in this molecule. Okay, so we've thought backwards. Again, in purple, I'm going to highlight the enolate portion of our molecule. And in orange, I'm going to highlight the alpha-beta unsaturated electrophile. Let's just go through it from the start and work all our way to the end. We'll just talk through it, okay? So, here's the molecule you're going to make your enolate from. You remove the proton to make the enolate. There's your enolate in purple. Purple alpha carbon attacks orange beta carbon of your alpha beta unsaturated carbonyl compound electrophile. And the negative charge goes onto the alpha carbon. That generates this product or intermediate, the new bond shown in red. This product is an enolate with a negative charge on the alpha carbon. We protonate that alpha carbon to get to the Michael product, the 1,5-diketone. Then we remove, and this is something we didn't draw, we remove this second orange alpha proton using hydroxide as a base. That will get us this enolate. Again, we can highlight in purple the portions of the molecule that come from both of our sources. That new enolate orange alpha carbon will attack the purple carbonyl carbon to get a tetrahedral intermediate. That's the first step of the aldol reaction. Then that negatively charged oxygen picks up a proton from water to give you the beta hydroxy aldol product. Then you deprotonate at this alpha carbon to get an enolate, which then eliminates to give you the Robinson annulation product. Okay? So that's mechanism, but that's also illustrating how you can break the two pieces together apart into the two component starting materials. That's going to take a fair amount of practice, so I encourage you to get started. Friday, we move on to the next chapter, which is on benzene.